This is the fourth part of the IPC Surface Mount Solder Joint Evaluation Series. In this videotape, we will be examining gull wing leads by discussing the major types of components that use this style of surface mount lead configuration. The first type we will be describing is the SOIC package. The letters SOIC stand for Small Outline Integrated Circuit. These SOIC surface mount components are basically a replacement for the dip or dual inline leaded components. Since surface mount leads don't require through-hole mounting, both the leads and the lands can be smaller and located closer together. SOIC leads are typically spaced on 1.27 millimeter centers, which allows twice as many component leads to be connected within the same given area. Some of the newer SOIC components have leads spaced on 0.63 millimeter centers and down to 0.4 millimeters. These are usually referred to as fine pitch components. Both the regular and the fine pitch surface mount components will have their solder joints spaced much closer together than the conventional through-hole components. This makes the assembly much harder to produce and visually inspect. The only place you can really see the entire shape of an SOIC gull wing solder joint is at the corner of the component. From this angle you can also understand where this particular type of lead got its name. A second type of gull wing component is sometimes referred to as a QFP, or quad flat packs. QFPs have gull wing leads on all four sides of the component package. QFP leads are typically spaced on 1.27 millimeter centers, and sometimes even closer. Centers of 0.635 millimeters are becoming more common. Finer pitches, even lower than 0.3 millimeters, with up to 184 leads or more, are now available. A device like this can replace more than a dozen 14-pin dual inline through-hole components. A third type of component with this style of lead is the SOT, which stands for Small Outline Transistor. SOTs come in various sizes and lead configurations. Some have 3 gull wing leads, 2 on one side and 1 on the other. Some have 4 leads. They may also have several different lead shapes. A fourth component type using the gull wing style is called TSOP, which stands for Thin Small Outline Package. These two-sided, low-profile components have fine pitch leads on each end of the package and are only 1 millimeter in height. Their size and density makes them increasingly popular in computer and other digital products. But a component with leads this small will be prone to handling damage. If one of these thin metal leads bumps into something, it will bend very easily. If just one gull wing lead becomes bent slightly upward, then the lead won't make physical contact with the land or the solder. The electrical connection would not be made, and the component may not function correctly. That's why these fine-pitch two-sided gull wing components usually come in specially shaped IC tubes, which are designed to protect the leads from shipping and handling damage before they're placed onto the board. Gull wing components with leads on all 4 sides will often come in waffle trays. The trays consist of a series of pockets which are designed to protect the leads from bending. Either way, most companies will check the coplanarity or levelness of the leads to make sure they won't have any tolerance problems during the soldering operation. Imagine a two-sided gull wing component that has a row of leads which are all bent down a few tenths of a millimeter. As long as this coplanarity problem isn't too serious, the component might just lean a bit towards the lower side and still solder properly. Now let's consider a 4-sided component, a QFP, with one row of leads bent down the same few tenths of a millimeter. This will cause the leads on both of the adjacent sides to angle upwards, leaving a gap between the bottom of the leads and the top of the lands. If this gap is large enough, we may end up with no solder connection at all at several of the leads. The maximum acceptable amount of variation between the highest lead and the lowest lead on all sides of the component is typically 1/10 of a millimeter. For example, if one lead is bent upwards 0.08 millimeters and another lead is 0.05 millimeters lower than any of the others, the total variation would be more than 1/10 of a millimeter. In this case, that particular component would not be acceptable. In addition to checking sample components for coplanarity of the leads, the incoming inspector should also make sure that the leads are evenly spaced and perpendicular to the body of the component. If some of the leads are bent or skewed to the right or the left, they won't line up properly with the lands on the board. Some automatic placement machines incorporate optical inspection systems to check for lead alignment and coplanarity before placing the component onto the board. There are no specific industry guidelines for the amount of allowable variation, other than meeting the general soldering requirements of Table 9-2 of the J standard. Each company will define their own acceptance criteria for skewed or bent leads prior to soldering. Let's take a break now to make sure you understand everything we've covered up to this point. In this next section, we're going to discuss some of the typical problems that can occur during the placement and soldering of gull wing components. Gull wing components can be attached to the board by several different methods. The wave soldering process can be used to join certain types of surface mount components to the board. However, the amount of available solder in the wave is considerably more than the volume of solder paste used in the reflow process. The chances of excess solder bridging across closely spaced leads is much more likely during wave soldering than during the reflow soldering process. Therefore, the solder reflow process is the more common method for attaching gull wing components. First, a specific amount of solder paste is stenciled or screened onto the lands. Then the component leads are placed into the solder paste. The tackiness of the solder paste will hold the components in place until the reflow soldering operation. Next, the assemblies are baked, usually as part of an inline process, to drive out any moisture or volatile solvents that may be contained in the solder paste. This helps prevent the formation of steam or gases in the solder joints during the reflow process. The reflow soldering process can be performed using infrared radiation, hot air convection, a combination of both, or in a vapor phase solder reflow machine. In any event, as the solder paste melts, it should wick up the sides of the gull wing lead, particularly at the heel. If the volume of solder paste is not sufficient, the shape and size of the solder fillet won't meet minimum size requirements. The heel of the gull wing solder joint is the most critical part of the solder connection. It's important to have a sufficient solder fillet at the heel to withstand the contraction and expansion of the circuit board. Whenever an electronic product is in operation, it creates heat, which first causes the part, and then the base material of the printed wiring board, to grow or expand in the X and Y directions. This stretching of the base material puts a tension or stress on the leads of the components, especially at the heel of a gull wing solder connection. Unless the heel has a sufficient amount of solder to withstand this expansion and contraction, the joint may eventually crack and cause the component to fail. Another concern about gull wing components is the visibility of the solder joints. It's almost impossible to see the entire fillet, especially at the most critical area of the heel, since the rest of the leads are blocking your view. The only place where you can see the entire shape of the heel is at the corners of the component. This means that on a component with leads on all four sides, you will only be able to see the shape of the heel fillets on 8 of the leads, 2 at each corner of the component. If the amount of solder on each of these 8 corner joints that you can see is acceptable, then all we can really do is assume that the rest of the joints will be similar to the corners. What you are better able to see on a gull-wing component is the alignment of the leads onto the lands of the board. This is important because misalignment is the other major problem with gull-wing components. It's possible that an occasional component can be positioned slightly off-center in either the X or Y axis by the automatic placement machine. The component might also have been placed at a slight rotational angle called theta. That would cause the leads to cross over the lands and become slightly crooked or askew. One or two of the component leads might also have been slightly bent during some point in the process. All of these causes of component misalignment will reduce the distance between the component lead and the land right next to it. If a misaligned lead actually makes contact with the adjacent land, we would have the wrong lead connected to the wrong land. A component with this condition may not function correctly. In other cases, the leads will extend very near to the adjacent lands but won't actually touch them. The acceptance criteria for this type of a situation depends on the type of assembly being built and the reliability requirements. There is usually a minimum electrical spacing requirement called out in every company's procurement specification. This dimension defines the minimum amount of clearance between any two electrical features on the printed board assembly. We will be reviewing the acceptance criteria from the ANSI J Standard 001 for gull-wing component alignment and fillet sizes in the next section of this tape. It also should be mentioned that there is a manual, the IPC A610, that makes a useful companion document because most of the solder joint criteria from the J Standard are graphically or photographically illustrated in the A610. A desk reference manual, the IPC DRM SMT, is also available and includes a visual summary of the dimensional acceptability criteria and sample defect photographs based on the J Standard and A610 specifications. Let's take another break at this point to review the material we just covered and answer any questions you may have before we proceed with the next section. Now we're going to take a look at the requirements in the J Standard 001 for gull-wing solder joints. Table 9-2 contains all of the dimensional alignment requirements as well as minimum and maximum sizes for solder fillets. Let's begin with the first requirement from the J Standard, maximum side overhang, or Dimension A. Dimension A is measured from the furthest part of the lead to the closest edge of the land. Notice that the lead can also be skewed at an angle or hanging evenly off the land all along the edge of the lead. Either way, the maximum side overhang of all three classes of assemblies is listed in Table 9-2. To quickly review, Class 1 is for general electronic or consumer products. Class 2 is for dedicated service or commercial products. And Class 3 is for high-performance, high-reliability applications. Class 1 and Class 2 requirements for Dimension A allow up to 1/2 of the lead, or Dimension W, to hang over the edge of the land, or up to a maximum overhang limit of 0.5 millimeters, whichever is smaller. This 0.5 millimeter will generally apply to the wider types of gull-wing leaded components, like inductors or capacitors, for example, rather than narrow ribbon leads. Class 3 assemblies also have the same 0.5 millimeter maximum overhang dimension. But in this case, the lead is only allowed to overhang 25% or 1/4 of its width over the edge of the land. Once again, the smaller of these two dimensions will apply as a maximum overhang limit. Any amount of toe overhang, or Dimension B, is acceptable for all three classes, provided it does not violate minimum electrical spacing between the lead and adjacent lands or components. The amount of allowable toe overhang will also be limited by the side joint length of the solder connection, and will be examined in more detail later on. A toe fillet, if present, is not considered crucial to an acceptable gull-wing solder joint, so it is not included as part of the J standard criteria in Table 9-2. The next dimensional requirement is the minimum end joint width, or dimension C. C indicates how wide the solder joint needs to be. This dimension can also depend on how far the lead hangs over the land, which we previously defined as dimension A. For Class 1 assemblies, the specification calls for a solder fillet that measures at least half of the width of the component lead, or half of dimension W. Notice at this alignment, the measurement is made at the midpoint of the solder joint, at the thinnest part of the fillet. An ideal gull-wing solder joint will have a slightly concave fillet on both sides of the lead, and will measure more than half the width of the component lead. In rare cases, where the solder only wets part of the land or lead, we want to make sure that the solder fillet extends at least halfway across the width of the lead. The primary concern is when the component lead is hanging over the edge of the land, reducing the volume of the solder. We always want to make sure that there will be enough solder to ensure the strength of the connection. Both Class 2 and 3 gull-wing solder joints have similar dimensional requirements for minimum end joint width. The solder fillet needs to extend the full width of the component lead, dimension W, less the maximum side overhang, or dimension A, which we calculated earlier. Essentially, this means that a Class 2 or 3 solder joint cannot meet the requirements for minimum end joint width if dimension A is too big. To put it simply, the minimum end joint width for Class 2 or 3 solder joints is dimension W minus dimension A. The next requirement is called minimum side joint length, or dimension D. Here we're looking at a side view of the solder joint. D is measured between the top edge of the heel and toe. You would rarely ever see a solder joint like this, since the solder will usually extend all the way to the end of the land, and obviously that's the preferred condition. What sometimes happens is that the toe of the lead could extend off the front edge of the land, as previously mentioned in the section on toe overhang, or dimension B. The amount of allowable toe overhang will relate directly to the minimum side joint length. Too much overhang and the side joint length will fall below the minimum allowed. Class 1 components must have a side joint length that is at least as wide as the lead itself, or dimension W. But once again, there is also a minimum dimension of 0.5 millimeters. This means that as long as the side fillet is at least half of a millimeter long, that would be acceptable for a Class 1 assembly. For Class 2 and 3 assemblies, the length of the side fillet must extend at least as far as dimension W, or the complete width of the component lead. The next two requirements have to do with the amount of solder at the heel of the component lead. Too much solder can cause damage to the component package. Too little solder may not hold up to the mechanical stress as the board grows and shrinks. The maximum heel fillet height, or the amount of solder in a Class 1 gull-wing solder joint, is not specified. The primary requirement is that a properly wetted fillet exists. You'll remember from all three of the previous tapes in this series that every solder fillet should have a contact angle of less than 90 degrees. The solder should also be feathered smoothly onto both the lead and the land. There is a requirement for the maximum heel fillet height, or dimension E, for Class 2 and 3 assemblies. The solder fillet may extend through the top bend of the lead, but should never touch the component package or end seal. Class 2 assemblies also have a requirement for minimum heel fillet height, or dimension F. The formula describing the minimum heel fillet is dimension G, plus 1/2 of dimension T. Dimension G is the thickness of the solder underneath the component lead, at the toe or the tip of the lead. Since some leads are formed on a slight angle, this requirement is evaluated at the toe of the lead, where there is the least solder thickness. 1/2 of dimension T is the same as half the thickness of the component lead. If we add up dimension G and 1/2 of dimension T, we get the minimum heel fillet height for Class II assemblies. Class III assemblies require a minimum heel fillet height of G plus T, or the minimum solder joint thickness plus the entire thickness of the lead. That's all of the dimensional requirements from Table 9-2 of the ANSI J Standard 001. It's a bit to remember, especially if you have to deal with more than one class of requirements. But it's really not as bad as it looks, since almost every solder joint will pass these dimensional criteria, and any variations that are extreme enough not to meet these dimensional requirements should be readily visible and easily analyzed. Some companies have a policy that requires corrective action when more than 0.3% of the joints inspected fail to meet the requirements from Table 9-2. The use of such SPC and other process controls to ensure consistently high-quality solder joints is much more productive than in-product inspection. In the next videotape, we'll be looking at J-leads, which are another common type of surface mount component. But let's stop now and make sure that you understand how to apply all of these dimensional requirements before we proceed to the next video.